Maintaining an internal body temperature between 38 and 41 degrees Celsius is an extraordinarily expensive biological commitment. For a bird to defend that temperature, it requires an energy input 30 to 40 times higher than a similarly sized reptile. This metabolic engine was forged over 250 million years. The process began with Triassic archosaurs developing constant body temperatures, followed by a Jurassic period marked by rapid miniaturization and the evolution of insulating feathers. By the time the Cenozoic era introduced massive global climate shifts, these feathered endotherms were forced to adapt to newly formed extremes, from high-latitude freezing habitats to scorching desert basins. To occupy these niches, a bird must continuously balance its own internal metabolic heat production against the fluctuating operative temperatures of its environment. Avian endothermy requires constant, active physiological management. Faltering for even a few hours means starvation in the cold or fatal overheating in the sun. This equation represents the absolute physical law of avian thermal survival. The total heat content of a bird, dq over dt, depends on the exact sum of heat gain and heat loss. 4 of these variables are dictated entirely by the environment. The bird exchanges thermal energy through radiation from the sun, forced convection from the wind, conduction with the ground, and evaporative cooling. To maintain equilibrium against those external forces, the bird autonomously manipulates the final term, metabolic heat production. When a bird sits on an exposed branch, it doesn't just experience the air temperature. It absorbs a combined environmental thermal load, an integrated metric we call operative temperature. To understand how birds survive the planet's harshest operative temperatures, we must map this physics equation onto the definitive Shalander-Irving model. This chart maps the baseline relationship between an animal's metabolism, its insulation, and the temperature of its environment. For a strict endothermic homeotherm, internal body temperature remains a flat, unchanging line, regardless of what the environment is doing. Beneath that, we find the thermoneutral zone. In this specific temperature band, the bird's baseline basal metabolic rate naturally offsets environmental heat loss without any extra effort. The left boundary of this zone is the lower critical limit. At this exact temperature, the bird has maximized its physical insulation, usually by fluffing its feathers to trap a boundary layer of air. As the environment drops past that limit, the bird is forced to rely on muscle shivering. This generates internal heat, resulting in a linear, upward spike in its metabolic rate. Under this strict model, extreme cold forces the bird into a mathematical corner. The temperature drop triggers a proportional metabolic drain, making survival a strict race against starvation. But the opposite end of the zone presents a completely different threat, at the upper critical limit. When environmental temperature exceeds the bird's own body temperature, radiation, convection, and conduction all flow inward. Evaporation becomes the only physical mechanism left to dissipate heat. Crossing that upper boundary triggers a steep, simultaneous spike in both evaporative water loss and metabolic rate. This happens because respiratory cooling, panting, is active mechanical labor. The very act of driving air over moist tissues requires muscle action, which generates new metabolic heat as a byproduct. This creates a deadly physiological loop. To survive, the bird must evaporate water faster than its own breathing mechanics generate heat. Small birds with high surface area to mass ratios simply cannot store enough fat to survive a steep metabolic climb on a freezing night. If they strictly defended the Shalander-Irving lower boundary, they would exhaust their energy and die before dawn. This graph illustrates how these birds employ facultative heterothermy, commonly known as torpor, to abandon that costly metabolic curve entirely. Torpor involves the deliberate resetting of the body temperature set point. By temporarily suppressing their metabolic rate, these birds revert to an ancestral ectothermic-like state. At an elevation of 3,800 meters in the Peruvian Andes, nighttime operative temperatures plummet far below freezing. This panel tracks a giant hummingbird surviving those exact conditions. Instead of shivering, it allows its core temperature to track the ambient air, plunging to a near-freezing 3.3 degrees Celsius overnight before recovering in the morning. By selectively abandoning endothermy, the bird removes the massive energetic burden of fighting the cold, conserving enough fuel to survive until the sun returns. On the other side of the spectrum, extreme heat requires massive evaporative cooling, but pushing air through a bird's chest cavity demands intense mechanical labor. This chart plots respiratory frequency against body temperature in heat-stressed birds, showing a clear division between type 1 and type 2 panting as the animal nears lethal thermal limits. During type 1 panting, the bird achieves evaporative cooling by sharply increasing its respiratory rate while keeping its tidal volume shallow. This ventilates the dead space in the upper respiratory tract without flushing too much carbon dioxide from the blood. But if body temperature continues to rise, the system collapses into type 2 panting. Respiratory frequency suddenly drops, tidal volume spikes, and the metabolic costs of deep breathing accelerate uncontrollably. The heavy reliance on standard respiratory muscles makes traditional panting inherently self-limiting. The metabolic heat generated by breathing creates a hard biological ceiling on heat tolerance. In hyper-arid environments like the Kalahari or the Australian outback, midsummer ambient temperatures routinely push past 50 degrees Celsius. Standard panting here would quickly trigger a fatal heat cascade. But birds in the order Caprimulgiferes, like nightjars, possess a highly specific mechanical bypass, gular flutter. Instead of using heavy chest muscles, these birds rapidly pulsate their hyoid apparatus and gular membranes at over 1,000 cycles per minute. This drives massive evaporation across the wet membranes of the mouth and throat. This upper trace demonstrates the exact efficiency of that adaptation, showing a massive spike in water vapor loss during a gular flutter bout, without any corresponding increase in carbon dioxide production. Because the mechanical cost of fluttering the hyoid is so negligible, the bird's resting metabolic rate remains completely flat, even as air temperatures soar toward 55 degrees. Nightjars completely decouple evaporative cooling from metabolic cost. They shatter the upper limit of the Scholander-Irving model, easily surviving heat loads that would cook a standard passerine. When we take these extreme physiological adaptations and map them back onto the baseline Scholander-Irving framework, we see that torpor entirely cuts off the steep metabolic climb required by the lower critical limit, replacing it with a dramatic, controlled temperature drop. And gular flutter flattens the right side of the curve, erasing the metabolic penalty normally associated with high-temperature evaporative cooling. Survival ultimately comes down to managing total thermal conductance, the physical rate of heat transfer across the bird's surface area at any given moment. Survival relies on the active, facultative manipulation of these heat flux variables, moving beyond the static boundaries of homeothermy. A bird's ability to bend these metabolic rules is a critical factor in how 10,000 species expanded into nearly every thermal niche on the planet. Millions of years of Cenozoic climate adaptation forced the avian lineage to solve both freezing blizzards and scorching desert suns. While anatomical features like the rete mirabile for brain cooling provide a baseline defense, it is behavioral flexibility and metabolic plasticity that truly dictate survival. By grounding our understanding in the strict thermodynamics of heat exchange, we can map the exact biological limits of avian physiology. Endothermy requires an immense caloric investment, but the ability to bypass its limitations allows birds to inhabit the globe's most extreme environments.